are now being connected to your conference. Hello.
Hi, how are you?
Hi, I'm doing good. How are you?
I'm okay. I just wanted help on two questions. So the first question was to let me actually get a better. So the first question was to find the integral of x e to the x squared dx, and I'd like to know how to do this with u-substitution.
Okay, so have you begun working on this specific problem?
I've been looking at u-substitution, and and I'm not too sure about what the benefits of u-substitution, or really the methodology of u-substitution. I'm not too familiar. I've looked around, but I feel like everyone is saying different things to some extent, and I'm just sort of confused with the concept of u-substitution.
Okay, so hold on. Let me open up a resource. Okay, so for integration by substitution is one of the basic techniques that we use when we integrate. So why do we say that we need to use u-substitution? So, for example, you have a derivative, or you have a function that underwent differentiation, right? So let's say that you have a function f. Okay, so we have a function f of g of x. Okay, so this is a function inside a function. So in order to differentiate the function, a function like this one, a function inside another function. So let's say we differentiate this. So we just need to demonstrate how this works so that you understand how we use the u-substitution for different problems. So.
And is f the antiderivative?
So let's say f of g of x is the original function. So we are not at the point where we integrate. We differentiate first, because we know differentiation and integration are different opposite processes or inverse processes of each other. So before we integrate, we need to see how it looks like when we differentiate. Okay.
So can we can we use maybe lowercase f? Because I think big F, they say, is the antiderivative. Maybe, I'm not too sure.
Of course. Okay. So let's use a smaller case f for this one.
Sure.
Okay. So let's say that you have a composite function. So this one is a composite function, since g of x is inside another function f of x. And then let's say we differentiate this one. So reviewing what we know about differentiation, if you have a function inside another function, what technique do we use to differentiate?
So we use the chain rule, where we find the derivative of the outside function and multiply by the derivative of the inside function.
Okay, so that is correct. So for this one, we use the chain rule. So we differentiate the outside, which is f of g of x. Okay. So these are the fundamental parts of this, so that we can understand. And then the derivative, of the inside, like that. Okay, so they
Sure.
are multiplied together.
Absolutely.
Okay, so how does u-substitution work for this one? So let's say that we have this function right here. So so we have the derivative function now. So now we are now going to get the antiderivative, or we now have to apply the integration to get to the original function, right?
Yes. I'm sorry. Could you repeat that, ma'am?
Okay, so we now have the derivative function right here. So we have done the differentiation.
Yes.
Now, to demonstrate how to use integration by substitution, we will use this derivative function and then integrate it so as to demonstrate how to use the u-substitution method.
Sure. Sure.
Okay, so let's integrate this part right here. So we have f prime of g of x multiplied by the derivative g of x. Let's say d of x is the differential that we have. So for this purpose, we have to use the u-substitution so as to replace your sorry. So we will let one of these functions as u. So because it is the u-substitution, we need to let one of the functions as u. So let's say let's say that we substitute
would you like to use, well, would you like to maybe use an example where maybe we have f of g of x? Because I think maybe u substitution is for the chain rule, right?
Oh yeah, so we did the chain rule right here at this part, right here, and then the u substitution will be used to, let's say, undo the chain rule that we have.
Okay.
Okay, so after this, let's give you an example so as to further demonstrate.
Sure.
Is that okay?
So we want to undo the chain rule. And we take what we have here, which is the chain rule. So to undo the chain rule would essentially be taking the antiderivative of this particular case. And you want to use the and see that's essentially the problem, because I don't think the product rule can be applied here, obviously, and I don't think there's a product rule for antiderivatives.
Okay, so for this one, since we need to use the u-substitution, we need to let the function g of x. So we need to let g of x because under the chain rule, we have this part right here.
Right.
Okay. And then we need to let the original function g of x as u. So let's do that.
Could we have chosen g of x here to be u? Basically what I'm trying to say is, could we have chosen g of x, this one, to be u?
Yes, so that is what we primarily choose, the g of x, because the f of g of so the f prime right here is already the derivative of your whole function. So we need to get let me rephrase it in another way. So we need to get the g of x. So this part right here, let me encircle it. So this part right here, under the chain rule, we do not change the thing that is inside the function. So let's say we have x plus 1 raised to 2. So under the chain rule, we have 2, x plus 1, and then the derivative of x plus 1 would be 1, right?
Right.
Right there. So as you can see, this will serve as your u. It does not it is not affected by the first part of your chain rule.
Absolutely, I agree. I agree.
Okay. So so that will be u. So we need to get the derivative of your du, or the derivative of your u, which is du.
But really,
du.
is it du or I think the notation that I've seen is d over dx to find the derivative of u. Can this be applicable as well?
Yes, so that is correct. Since you are differentiating the function u with respect to x, so that is absolutely correct. So you are differentiating u with respect to the variable x.
Okay, so we can rewrite this as being, yeah.
So this one will be g prime of x, since we don't really know what g of x is. So we will denote it as g prime of x.
Right.
And then we know that this part right here, looks a little something like the du with respect to dx. So if we multiply the dx to this side, we will have du is equal to g prime of x dx.
Well, is there any reason, so if I could sort of backtrack here just for 1 second. So this particular portion here, we said was the chain rule. And then you said that we want to undo the chain rule, which would be finding the antiderivative. And over here, it seems like you took a variable, which was u, and you made it stand for the inner function gx. But then it seems over down here, you're solving for du. Is there any reason as to why you do this step here?
Yes, so because you have the derivative of the inner function right here, g prime of x dx. So so essentially we are looking for the derivative of u with respect to x, so that we can replace this with a single differential du, which is this one. Okay, so after multiplying dx to the other side, you will get this, and we can replace this whole thing with a single differential du. Okay.
So you're taking dx to the other side, because of what exactly?
So we need to replace the derivative of your inner function and then the differential dx with a single differential du.
Okay, I understand.
Okay.
Sure.
Okay. So if you replace g prime of x dx with du, you can also replace g of x with u, since we have this part right here. So essentially we have the integral of your f prime of u du. Okay?
Right.
Okay. And then this is general for any of the integration formulas that we have. So it means that for this one, you can use, so the derivation that we did right here is like how the u-substitution works, and then this works for any, let's say, any integration formula that we have. So this will give you, since this is a general denotation, so we can say that the antiderivative of f prime u will be f of u plus c. And then this goes back. So since this u, let me encircle it. Since this u is equal to g of x right here, we can essentially write this as f of g of x. Okay? So this is the same as the function that we originally started, which is this one at the top, this one. Okay?
Sure.
So I think an example would be better. So let's see if we can have an example right here.
I can put down an example if you'd like.
Okay.
So let me go to whiteboard 2, maybe.
Mm-hmm.
So we want to find, so this is whiteboard 2 here. So let's see. So we want to find the integral of cosine 6x
Mm-hmm.
dx. Is this a good example?
It can be. So this is one of the simpler examples for your u-substitution.
Sure.
Okay.
Yeah.
So we have two functions right here. We have cosine, let's say cosine of x, and then we have inside cosine of x, we have 6x, right?
Right.
So we always take the inner function. We always take the inner function to be u. So the inner function will be 6x. Okay. So let's let u be equal to 6x.
Sure.
Right there.
Sure.
Okay, so taking the derivative of u with respect to x, so we have du over dx, the derivative of u with respect to x. So what do we get as an answer?
So are you taking the derivative of both sides?
Yes, so since we are differentiating u with respect to x, so it is like dy over dx. So if we have the derivative of y with respect to x, the equation that you have is an equation of y in terms of, let's say, x. Okay, so this is the same as u is equal to 6x.
Okay.
So
okay, so 6 would be our derivative, or I guess let me just write this as so this would just be so this would be du over dx, which would equal 6. And it seems like you want dx in terms of du. So that would be, so we would do some transposition, and we would get 6 dx. And
okay, so,
yeah.
Okay, go ahead.
Oh, that's pretty much all I have to say.
Okay, so as you notice right here, we have a constant 6 right before dx.
Right.
So in the original function that we have, we do not have a 6 multiplied to cosine 6x. So what we need to do for constant like this, so the only thing that we have for the only thing that we have in our function is dx right here. Okay.
Right. We have yeah. So du is now written in terms of dx. Yeah.
Okay. So we are getting there. So since we have 6 right here, 6, it is a constant, but we do not have any 6's multiplied to either cosine 6x or dx. So since this is a constant, you can go ahead and divide both sides by 6, since we only need dx. Okay?
So you want dx in terms of du. So you're dividing by 6.
So it depends on how your function looks like, but this is what we do if we have constants for this one.
Okay. So dx would then, of course, equal du over 6. So now we have dx in terms of du, so we can write f of, or we can write the integral the antiderivative of being 6x du over 6.
So at this point, you can now change the inner function as u. Okay, there we go.
Okay.
Okay, so what is our rule when it comes to constants? So what is our rule when we are integrating constants?
The rule is that the constants, so the integral of k dx is equal to kx.
Oh, sorry. So, so that is correct. So if we have k dx, so if we are differentiating a constant by itself, we have k dx, kx. So what I meant to say was, what do we do if we are integrating a function and then you have basically a coefficient. So 1/6 is basically a coefficient to your function.
Like this? So we can pull out the constant.
Okay.
Just like this. So I guess this can be written as 6 to the negative first du.
Okay, so you don't, so 6, it is 6 raised to negative 1, but you don't have to do it like that. You can just take the 1/6 out of the integral sign.
Okay, that I think is a little more simpler.
Okay.
Actually, I'm taking the integral, right? So I don't need to actually write this notation.
Okay.
So I think I'm just going to say 1/6 sine of x, or sine of u. Should I write du?
So we are already done with the integration. So this is now your answer. Okay, so don't forget the constant at the end always. Okay, there we go. So the goal with u-substitute. Is everything clear for this example?
Everything is clear. I have the steps down. The only thing that I'm just a little sort of hesitant on is why we do this process here.
Which one? Why we take the derivative of u?
Yes, why we take the derivative of u and also the derivative of 6x. So this entire actually the only problem really is why we are choosing to do this.
Okay, so we set the inner function to u, and then part of the process is to get the derivative of u with respect to x. So the reason why we do that is to transform your function into an integration formula that we recognize, like what we did with this one. So this is an integration formula that we recognize.
Yes.
And then we easily integrated cosine of u as sine of u plus c.
Right.
And then we just substituted back the value of u, which is 6x. So the main reason is that we need to transform your original function into an integration formula that we can easily recognize.
Well, the thing is, if I completely understand that the point of u substitution is to sort of transform our integral into something we know how to compute. But suppose I had, let's say, u is equal to 6x. Let's say I was right here, and then I just said, okay, f of cosine of u dx, right? Right. So I'm trying to get rid of dx. I think that's what this whole attempt here is, to try to get rid of dx, I think. And is that the reason as to, like, this would be wrong, right? We can't have u and x, I think, maybe. Is that why we're doing this process?
Yeah, so that's also part of the reason why we find the different derivative of u with respect to x, is because we cannot work with integrating cosine of u while the differential that you have is with respect to x. So these are different variables. U and x are different variables, so we cannot work with that unless the variables are all the same.
Okay, so our goal was to get dx equal to something of du, so that we can substitute back into the integral question. So we're just trying to write this in terms of u.
Yeah, that is correct. And then also you need to recognize the other parts of your function if they also belong to dx. So let's see. Okay, so I will be showing you an example of the thing that I was talking about. So
Sure.
let's say you have to integrate. So we have to integrate x squared plus 1, and then the whole thing is raised to 50 multiplied by 2x dx. So we do have a lot going on with this problem. We have a problem inside, or we have a function inside another function, and then it is multiplied to another term, 2x.
Yes.
So what will be the u for this problem?
So the u for this problem, I was told here and there that I can only choose a u whose derivative is in the integrand.
So that is correct. So you should take the function. You should let a function u, wherein if you took the derivative of that u, you will be able to get the derivative inside the integrand.
Right.
So it is part of the function that you are working with.
But that is not the case in the previous example.
Yes. So because so it doesn't matter for the other example that we have, since the derivative of 6x is just a constant 6.
Yes.
So for constants, we can easily maneuver through functions like that, wherein if you took their derivative, you will only end up with a constant value.
Yeah.
So it's easier to work with those.
Sure.
And
sure.
Because we can easily take the constant value outside of the integral sign, right?
Absolutely.
Like what we did with
absolutely
1/6 right here.
Very true. Very true. So I guess our u will be x squared plus 1. And And then, of course, du will be equal to x squared plus 1 dx. And, right?
We need to differentiate your u.
Oh, right, of course.
Mhm.
So this would be 2x dx.
Okay.
And then, of course, we can divide by 2x. So dx is written now in terms of du. So we can have this as being u to the 50 2x du over 2x. And these would cancel out. So we would have u to the 50 and, of course, du. And then once we take the integral, we can just say that we have x plus 1 to the 50th power, which if we do reverse power rule, that would just be x plus 1 to the 51st power all over 51.
Okay, so this part you did it correctly, except for du, it should be dx since you reverted, you plugged in the x plus 1 back into the integrand. And also, take note of the function that you are working with. This could get you in trouble since you have x squared plus 1 and then you only wrote x plus 1.
Okay. Sure. So if this was x squared plus 1 here, this would be right?
That is absolutely correct. And then add the constant at the end.
So if I input x back into the integral, I have to revert back to writing finding the antiderivative in terms of x.
Yeah, because you are working with a function in terms of variable x, so it means that, oh, sorry. Okay, so this is actually a little troubling, this one right here. Since we don't really substitute the value of u until we finish, until we are done with the integration, okay?
Yeah.
So we prefer to be integrating it in terms of u. So if you are integrating in terms of u, you should have u raised to 51 over 51. So it's the same thing, but this is the preferable way, in my opinion.
Yeah.
And then, since you are done integrating at this point, you can now substitute back the x into the u, the x squared plus 1 back into the u.
Right.
So don't go back to, don't plug back the value of u unless you are done integrating the whole thing.
Okay. Sure.
Okay.
Absolutely.
So I also like what you did with this part right here, right? Since as you can see, you already have du is equal to 2x dx right here.
Right.
Right. So at this point, and then this part is already present in your function right here.
Right.
So you can either do the method that you did, or you can just go ahead and replace this whole thing with du. It's the same thing, but both ways I think is preferable as long as it cancels out the 2x that you have right here.
Wait, so you're saying we can replace the whole thing with du over 2x, or just du?
Just du, because the derivative of u is, so we have du is equal to 2x dx. So this part right here is already present in your function, which is this one.
Right.
Right?
Yeah.
And then you can go ahead and replace this whole thing with du, since that is equal to du. But the method that you did is also a good way on how to replace the du, or on how to replace the dx with du.
But see, the thing is, du, okay, yeah, I think you're right. Du is in fact, because I think if I were to take this part here, and move this to the other side, then du would in fact be 2x dx. So I could either put du, or I could either put 2x dx. Since they're both equal, I guess it doesn't make a difference. Okay.
Yeah, so that is correct.
Okay, that sounds fine. Let me just pull up one more example here. Would you like to do that?
Or would you maybe like to work on the problem that you presented earlier?
Sure. Yes. Actually, I forgot about that entirely. So moving back to whiteboard 1, actually, this was the problem that I was just going to present. But here, I guess our u will be x squared.
Okay.
And du will equal 2x dx. And if I want to have write dx in terms of du, then dx will equal du over 2x.
Okay.
And so I can say that we're actually taking the integral of x e to the u du over 2x, and cancel out the x. So I'm actually taking the integral of e to the u du.
Okay.
And
so what about this 2 right here?
Over 2. And since the derivative of e to the x is e to the x, then the reverse is also true for the antiderivative. So I just have e to the u. I would have e to the u over 2, which would essentially be e to the x squared over 2 plus c.
Okay. So hang on just a second. Let me see. Okay. So that is correct.
Okay.
Okay. So you did better with this one. Just don't forget about the coefficients that you have.
Right. Absolutely. Okay, sounds good. So I think I'll definitely reflect on this here, and take it forward with me.
Okay.
Okay, awesome. Well, I'll let you know if I have if I have any other doubts.
Okay.
Okay. I hope you have a good night.
Okay, you too. So is everything clear?
Yes, absolutely. Yep, absolutely.
Okay, great.
Thank you so much. I appreciate your help.
You're welcome. Have a nice day.
You too.